Hello everyone, welcome back to our YouTube channel Becoming a ROS Developer. I'm Desire and today we have got Navjot. We has just completed the course ROS2 Basics with Python and he will be giving us the presentation of that. So what I'm going to do is I'm going to hand over the platform to him and then allow him to begin his presentation. Alright, whenever you're ready Navjot.
Okay. Hi everyone. Today I'm just going to present the ROS2 in 5 days the project. It's a part of the ROS2 in 5 days course.
Mm-hmm.
So I would like to thank the construct for providing me the opportunity to present this project. And let's start now. So it's
Thank
like
you.
the yeah. So the project is about there is a robot and the robot has to make use of its lidar to detect the nearest wall and then align to it and then just start following the wall itself.
So
So it's like an
I Navjot,
autonomous. Yeah,
so
sorry.
can you maybe reduce the size of your slides a little bit? Because I see them, but they are cut, right? So maybe
Now it's
yes,
fine.
but yeah, but your screen is cut. Are you not sharing a snippet of your screen? That
Yeah,
might
actually,
yeah, yeah, that might be the reason. So you need to share the full screen. They need to come all into perspective.
I think this option is not working now. The stop share. I'm trying to stop this share button and it's like
Hmm.
not working.
All right, all right. Let's see what we can do here. All right, open your slides one more time and try using control negative. Um, yes. So I want to see if your screen would adjust to fit.
I think there's some issue with the Zoom. Actually, it's like I'm
Ah,
not
okay.
able to stop. I'm not
Hmm.
able to like stop the screen sharing itself.
All right. Yes, we can go now. Maybe let's start from the top of the slide. Yes. You can also use Control Plus for your browser in case it's not visible.
Okay, okay, sure.
Yeah.
Thanks. Just
Okay.
let me know.
Yeah. Okay.
Shall we start?
Yes, let's start.
Yeah. Hi everyone. Today I'm just going to present the ROS check. That's part of the ROS2 in 5 days course.
Mm-hmm.
So I would like to thank the construct for providing me an opportunity to present my project. I have already finished the course. Now I just today I'm going to present it. So what's the objective of the project? This project is based on like we have to build an autonomous wall following robot
Mm-hmm.
and main objective will be like for the robot that it will use its lidar data to find the wall that's closest to it.
Mm-hmm.
Then it's going to align towards that wall, and finally then it will start following the wall, and side by side it is going to track the odometry as well.
Mm-hmm.
So how I implemented this project was in the starting I studied about lidar fundamentals, did some research and created two basic scripts that helped me to understand the lidar data of the robot,
Mm-hmm.
because that was the initial step before programming the wall following and wall finder. So I used like finite state machines in this project and hysteresis because I will just explain them what I did, because they helped me to make the robot motion smooth.
Mm-hmm. Okay.
So I just the first part of the project is to create the wall follower robot, and the second part is the to create the wall finder one, in which the robot will find the wall, and the last one is to uh, uh, create a new node that records the odometry while the robot is following the wall.
Mm-hmm. Mm-hmm.
So I started with the lidar fundamentals. Initially, it was a little bit challenging for me, but then so finally I decided to create two scripts that help me to understand the laser data and inspect it, and then convert the angles into the indices, which I will soon be coming into.
Mm-hmm.
So this is just the like sample of what I did was like created two scripts. After that, the output is like that. So it provides me the lidar data, like for example, say what's the minimum angle of the lidar for this robot, what is the maximum angle, what's the total scan number of total scan ranges, what's the angle increment and the field of view.
Mm-hmm.
So
Mm-hmm.
that's how I did it. Now let me show you in the practically what this does actually does.
Mm-hmm.
So in the terminal one, I have already opened the simulation. And for the terminal two, cross to run lidar. utils. So this is what it does, is
Mm-hmm.
just once I run the script, it shows me all the data of this robot.
Mm, mm, okay.
And if I go to the script itself, it's this. I just simply subscribe to the laser data, and then I defined the laser scan callback function,
Mm-hmm.
in which I just defined all of them and then finally printed all of them. That's very simple thing that I did. The another very important utility function that I used for programming this robot was laser utils. This function, I simply just used like how to get the index from the angle. So
Mm-hmm.
what does exactly that means is like this. I just generated this image to further explain the thing. So let's say this is the robot. This is the front side of the robot. This is the back side. It's the left and the right. And
Mm-hmm.
they all have angles. Like the right side is -90, front is 0 degree, left is 90 degree. So this is the lidar, like top on the top of the robot. And now the thing is like these are the angles. Let's say if I want to know what's on the left side of the robot, that will be left. I will have to use the particular index of the lidar
Mm-hmm.
that
Mm-hmm.
I have to convert from the angle. And how that happens is using this formula. Index is equal to integer I have converted into angle in radians minus minimum scan angle divided by scan angle increment. So it gives me the index at particular angle of the robot, which will in turn help me find out what's on the left side of the robot. For example, let's say on the right side, rear or front.
Mm-hmm.
Okay,
Okay,
let's move
so
on now.
I think if we go through the slides right now, we're going to run out of time. So let's do this. Connect to the robot
Mhm.
quickly, and then you show us how it works on the real robot so that we don't run out of time. Then we'll come back to the slides.
Okay, okay. So do you want to see the simulation as well or just the real robot itself?
Real robot itself.
Mm. Okay, okay, sure. So let's quickly connect to the robot
Mm-hmm.
and the bookings itself. Let's connect. So here is the real robot, and now I probably show like how it actually
Mm-hmm.
works. So we go to the workspace, and the first thing that we will do is I will just try to. So the first step for me here will be to show you how is the wall working, the
Mm-hmm.
first part of the project.
Mm-hmm. Okay.
So let's get close to the wall.
Are you saying when it's in the center it won't work, or if you tried?
No, no, it works, but the thing is like the first part is like we already I need to align the robot to the wall so that it starts following the wall directly. The second part is in which the robot will actually find the wall. But in the first part, it's like we have to align it with the wall and it will simply start following the wall. So that's why I just manually brought it close to the wall so that I can show you the part one of the project, which is like
Mm.
how it follows the wall.
Mm. Okay, so you split the parts. Okay, ideally we want you to
Yeah, yeah,
combine
yeah.
them.
Yeah, yeah. Okay, yeah, because it's like step by step I did everything. So the part first is like, yeah. So this one is the robot is simply going to follow the wall itself. I think it's getting stuck. Yeah.
And what's causing that? Can you preempt to that? Or what you think might be causing that?
It was working until now. Sometimes it like it shows like this if the robot is not like smoothly working. So even if I use this one, it's the robot should be working quite smoothly. Then only it works. If you see, I'm trying to control it, but little bit sometimes it's like it needs to be properly like it needs to be quite smooth if. it has to work. Otherwise, sometime it look now it started working. So it's
Mm-hmm.
like so this one is the part first of this project in which the robot has will like follow the walls simply. So it was yeah. So it will not go too far away from the wall and not go too close to the wall. It will keep in between.
Mm-hmm.
And when the wall in front comes, it will quickly turn to like avoid the front wall. And it
Mm-hmm.
will keep following the right side wall. Yeah. So it's like the part one. Shall we move to the part two now?
Yeah, okay, let's move to part two. Yeah. There's a number of things that I want to speak about, but let's move to part two and let's see how that works.
Okay. Okay. So I've stopped it. Okay. So that was the part first only. Now
Mm-hmm.
the part two is in which the robot will actually try to find the wall by itself and then align to it and then start working.
Mm-hmm. Okay.
And now I will show that. Yeah. So ROS2 main. So it has all the wall forward, wall finder, as well as odometry
Oh, okay,
recording as well.
all right, I see that.
Yeah. Yeah. So the robot will first align to the wall. Now it's aligning with this right wall.
Right.
And once it is aligned properly, then it will start working. And you can see here odometry is getting recorded,
Yeah,
like the
yeah.
distance it's traveling. Once the complete lap is done, then it is going to show all the odometry points, X,
Mm-hmm.
Y coordinates
Mm-hmm.
that it
Mm-hmm.
moved. Yeah.
Okay, okay, okay. So this part actually combines what the previous script is doing with the find wall service. Okay.
Yeah, that's everything in it. Wall finder, odometry recorder, wall follower, like step by step,
Okay,
like
I
the
see.
last.
I see why
Yeah.
you wanted to demonstrate it bit by bit. Okay, that's good. That's good.
Yeah. That was the so like I wanted to do step by step actually.
Mm-hmm.
So still like it's like approximately 5 meters when the lap is completed. Once the lap is completed, and it's going to show the all list of all the odometry points that it traveled.
Okay.
Yeah, this one.
Okay, so I'm guessing you meant 5 centimeters, right? Not five, not 5 meters.
Yeah. Yeah, so one lap, that's it. It's then at the end of the lap, it's going to show all the odometry points.
Automatic points.
Yeah.
Okay. All right. So
Yeah.
t tell me something. You spoke about using hysteresis, right? So can you explain a bit more why you needed that and why you had to induce some form of hysteresis?
Yeah, so in hysteresis, it's like before when I started this project, I was using just one reading. Let's say when the robot comes in the close to the front wall.
Mm-hmm.
So I had kept like if the distance is less than 0.5,
Mm-hmm.
just turn quickly. But the thing is, if we use the single ray index, sometimes it can cause disturbance.
Ah, I see.
Like it
Okay.
might like fluctuating values or something. Because
Right.
of that, the robot was not smoothly turning. So I did some research and everything. I wanted the robot to turn smoothly while changing from one wall to another instead of jerking or like oscillatory motion and that.
Ah, I see.
So that
Okay.
was the main reason I used hysteresis. So like a range. So try to turn the robot when it's like front wall is at 0.5
Yeah.
and just exit the state once it's more than 0.55. So it's like the robot will not continuously change states quickly, and that gave me the smooth motion. So that was the reason I used hysteresis specifically.
Mm-hmm. Mm-hmm. I see. Very, very nice. Okay, so let me ask you like a question that will probe into that idea. Right. So my assumption is you have a
Uh-huh.
an if then else a system that's working as your control system, right?
Yeah, if has exactly in the callbacks and everything. Yeah.
All right. So do you think using a proportional controller would have made it better than the hysteresis approach?
Probably, yeah, because I have studied a little bit about that proportion, but to be honest, I wasn't like I didn't have too much in-depth knowledge like how to implement that exactly.
Mm-hmm.
I know
Mm-hmm.
that's much smoother, way smoother than this approach. So, but I didn't have like enough knowledge about that one. but so that's why I didn't implemented that proportional controller
Yeah,
idea.
yeah.
But I think that would probably be much smoother even.
I like this one. It's good. It works. And the thing is, you realize that there was an issue here which you had to deal with, right? And you found a solution, which is really good. So, um, with the proportional controller, it will probably be maybe a lot smoother. But for the purposes of
Yeah.
what we're looking at, this is actually very good because it manages to meet that 5 centimeter plus or minus, right, stopping distance,
Yes.
and it matches it um, like there and there on the first try. So that's good. That's good.
Moreover, I used instead of single array, I used sectors because in the lecture notes itself,
Hmm.
we were using sectors. So I am not using single array. I'm using instead, like I spent a lot of time on this project to build those sectors and
Hmm.
everything. I am using sectors. So like multiple indices. Let's say if the front left and front right, I have divided here, and accordingly I just use it. I'm not using like a one single array, I would say.
Hmm. Yeah,
So
that's the correct approach. Actually, you're supposed to use the range of values, right? Otherwise,
yeah, so like this in the sectors I have defined front left, front right, left right. So it's like more like indices and ranges. So it's also it. I was doing tuning and everything, and I found out that this approach is like robot is much smoother if you
mm,
use average of indices a sector instead of a single array.
hmm,
So
hmm,
that's why I divided into sectors and use this idea to uh, perform wall following.
well done. Yeah, well done. Okay, let's switch to the slides quickly, and then we can finish with some details from there. Yes.
Sure, I just already explained like I used FSM state machines like one at a time, lidar distances, and challenge there I have just put few of the challenges that I used. It's like single lidar array caused unstable wall following that I already just explained. So I
Mm-hmm.
used sectors that I already showed in the script. Hysteresis I already told like instead of a single like number I used like a range of number from 0.50 to 0.55, let's say, to
Mm-hmm.
enter and exit the front side. Yeah. So
All right.
lidar, yeah, all this was done to reduce the lidar noise because I saw it was too much jerking and vibrations. I wanted to. So this was the second part in which I used this for wall finder node. Programmed it very similar. Like I used the custom find wall. I created the find wall service. I created the server, and
Mm-hmm.
then I used the client to call this service. So when the project starts, the initial part is like this service will be called so that the robot starts trying to find the wall,
Mm-hmm.
nearest wall. Yeah, so I just kept the small screenshot from the what I did. Front left index front. So it's like the sectors. So I've defined in the front sector, the left sector, the right sector, and then I used that function that I already showed, that get index from angle.
Mm-hmm.
So
Mm-hmm.
just once we put the angle in this particular scan range,
Mm-hmm.
and then I already face few challenges. So because in the real robot in the lab, the rear side always shows the one reading. So therefore, I'm in my scripts I have ignored this rear side because I think there's probably something mounted on the rear side of the robot. It always
Mm-hmm.
shows the same reading. So
Yeah,
I asked the construct.
I was going to ask you,
Yes.
do you know what was causing that? So yeah, it's something that's mounted on the robot. It's actually the rod that brings
Yes.
power to it. Yeah.
Yeah, because using this concept, it was always showing rear as the closest side.
Yes,
So I
yes.
had to. So the last part was to compute the autometry and everything. So in
Hmm.
this one,
So,
I used like math. Yeah, sorry.
all right. So before we move to this slide, there's something that I
Mm-hmm.
wanted to ask you on the previous slide. I thought I might forget. No, the one that
Yeah, yeah.
shows the challenges. You spoke about using finite state machines, right? So I want to understand, and for the purposes of those who are watching, why did you have to implement finite state machines, or why did you have to think about the tasks that the robot was doing in terms of states, right? Because I think that's a very important concept in this
That is
particular
a very
project.
important concept, and that concept is something that made the robot like literally very smooth.
Mm-hmm.
One second, just let me come to the.
Mm-hmm.
So this is the wall follower script. Okay.
Mm-hmm.
So when the robot is following the wall, there are like, let's say, only the two states that robot can do. Either it's like just avoid the front wall if the front wall is too close,
Mm-hmm.
or the other state can be to just follow the wall, the right wall. I mean, just use. So the thing is like, I wanted the robot to do only one thing at a time. So the robot is essentially going to check first which state it is exactly in
Mm-hmm.
using the lidar that readings. And I don't want the robot to quickly switch the states. Let's say for 1 second it's on the avoid front one, and the second time step it's like in the wall follow, because that was causing like vibrations and oscillations for the robot.
Okay,
So
so all right. So here's a follow-up question to this, right? So you implemented a find wall, right? And you implemented it as a service, am I right?
no, this was the wall following. It's the first part, like not in the service. It's in the wall following, the first part of the project, the wall follower one.
All right. So so this switch between the transition from finding the wall to following the wall was the one that you wanted to make sure that it switches and it commits to that state.
Yeah, so it's like the robot was quickly switching from like states in between. I didn't knew where exactly the robot was exactly, and the thing is like, if there is no, I wanted the robot to follow for one state for certain time. So
Mm-hmm.
I wanted the, let's say the robot was in this state, avoid front wall. So
Mm-hmm.
let's say the robot is avoiding the front wall. I just don't want the robot to quickly jump into the another wall follow. I
Ah,
want the
okay.
robot to only jump to the other state only when this particular condition is
It's satisfied.
satisfied.
All
So
right, all
this is the
right.
exit condition. So only one state at a time will mean the robot is just following one state at a time, which uh, which will not cause confusion, and the trajectory that robot will take will be very smooth because
I
of that,
see. All right, I see.
because
Now,
the lidar readings are very just like noisy. So
uh-huh,
I
uh-huh.
wanted to compensate for the tolerances and everything.
Now it makes sense why you say it's smoothness, right? Because every time it changes, it turns the corner, right? There's an abrupt change in lidar scan readings, right? So you need to make sure you tell it that it's turning the corner right now. It's not attempting to follow the wall. All right, all
Yeah,
right.
just do one thing at a time. If there is a wall in the front, just forget that you have to follow the wall.
Mm-hmm,
Just make keep track of this state. Just try to avoid the front wall side. Once you are sure that you have already finished this phase,
mm-hmm,
then the this condition will be checked. Let's say if it's more than 0.55, the
mm-hmm,
hysteresis that I already explained, the robot will exit out of this condition and just straight away jump to this condition in the next callback.
mm-hmm, mm-hmm. Wonderful, wonderful. Job well done, Navjot. Okay, so let's go on. We've got about 4 more minutes left, so let's finish the slides.
Sure. So this is what I did in the wall finder and wall autometry. So this is the last part of the ROSDECT. It's simply like we have to keep track of all the data points, the coordinates, X, Y, and Z. Not only, sorry, only X and Y, not Z,
Mm-hmm,
to so that which points did it follow, because it was the task to record all the odometry points,
mm-hmm,
the path through which the robot was moving, and at the end of the lab just give the list of all those points. And because it's a two-dimensional system, so we can't directly compute distance. Instead we have to use Euclidean distance, which we have to use hypotenuse, base
mm-hmm,
square plus perpendicular square. This is the Euclidean distance. So let's say this is the first point where the robot was, and next second robot is here. So what I did was, one robot goes from here to there, just keep this distance. Okay, just keep on adding this distance.
mm-hmm, mm-hmm.
And finally, like that's why it shows in the like odometry, like how much is the total distance. Just keep adding all of this between two consecutive points, one to two, two to three, and keep on. That keeps on happening. And I just
Yeah.
added all that to the list, and it shows.
All right. All right. So can you explain one more thing, right? So when you make reference to Euclidean distance, right, you show that you are measuring the shortest distance between 2 points. However, there is a
Yes.
point that I
Yeah.
think you must clarify in a bit more, right? Where is this shortest distance being measured, right? Because if we look at the whole lab space that we have, right, we could just say measure the distance from corner to corner, and you say that's where the robot has traveled, right? So can you explain more which distance exactly, or to what degree, or to what scale are we measuring this Euclidean distance?
So it's like essentially the two coordinate system. It's like because the robot is working in like two-dimensional space,
Mm-hmm.
and it's just following the trajectory. Let's say here on this two-dimensional plane.
Mm-hmm.
Let's say this is the first point where the robot is starting. Okay,
Mm-hmm.
so from here, let's say the robot moves from here to here
Mm-hmm.
because it's essentially wall following. So let's just say the robot moves from here to here.
Mm-hmm.
Okay, so this part where the robot started from has some particular XY coordinates.
Right.
And
Yes.
when the robot reaches here, it has another XY coordinates.
Exactly.
Okay. So because this is a two-dimensional space, I cannot simply do y2 minus y1 or x2 minus x1. So
Uh-huh.
in this
Uh-huh.
case, when there is a two coordinate system like here, x axis, let's say, and y axis,
Mm-hmm.
in this case, we have to particularly use like the distance called Euclidean distance.
Yes.
So what I did was, let's say the robot goes from here to here, and then here to here, here to
Mm-hmm.
here, these points, I just kept on calculating all these distances and
Mm-hmm.
then just stored them in the like odometry recording. So it just shows through which coordinates points the robot is going. And
Mm-hmm.
at the end of the lab, once it goes all the way around, comes here, back here, it just
Mm-hmm.
simply shows the list of all the
The
coordinates that robot followed and adds up the distances as well from time to time. If you see while following, it will add this to this to this to this, and it will show it has traveled 1 meter. Sorry, it has traveled 2 meters, 3 meters, 4 meters, five
mm-hmm.
meters, like that.
Mm-hmm. Wonderful, wonderful. Thank you very much, Navjot. So, warm round of applause to you for giving us a great overview
Thanks a lot. Thanks a lot.
Sure, thanks to you.
See.
All right, everyone, this was Navjot's presentation, and I would like to encourage all those of you who would want to try this ROS2 basics in 5 days using Python, right? You can take the course on our site, and then you can also come and showcase your project, and then you get an opportunity to get a certificate for it. So, until next time,